Let's talk about the remainder theorem that goes with the integral test. So this theorem says the following. If you have a series, the sum from 1 to infinity of ak, so this is just the stand-in for whatever the formula is. If that is convergent by the integral test, then a couple of things can happen. So before I keep talking, I should say convergent by the integral test not only means it's convergent, but it also passes all the conditions of the integral test. So positive and continuous. Okay, so if it's convergent and you can show it using the integral test, then the first line here says you can approximate the total sum with a partial sum. And this has nothing to do with the integral test. This is true for any convergent series. You can approximate the full sum with a partial sum. So whatever n is here, you're adding up the first n terms and saying, oh, the sum of infinitely many of them is roughly this total, right? So total sum that we're calling capital S is approximated by a partial sum, which we'll call S sub n, where n is the last term that you actually added in. Okay, so assuming that you are estimating your total sum with this computable partial sum, and we're calling the remainder R sub n the difference between the two. So this is the total sum that we can't exactly compute. And we're going to subtract out the partial sum, our estimate. So we want this to be very small, right? The better the estimate this is, the smaller this difference will be. So that remainder, or like error of the estimate, is between these two calculations. So as a lower bound, we have the integral from n plus 1 to infinity of f of x, where f of x is just the continuous function version of your series. So this is from 1 to infinity what you would have integrated to do the integral test part. So that's the lower bound. And then the upper bound on this error is the integral from n to infinity of that same function. So these are both improper integrals. And the n matches the subscript here. So if you have, let's say, the 10th partial sum, you're adding up the first 10 terms of the series to approximate the full sum. And you're saying, all right, that error between my guess and the exact answer is no more than the integral from 10 to infinity of the function. Now, having a lower bound on your error is not particularly useful. So typically, we only use this part of the theorem, although both parts do matter and you should know them. All right, so there's two classic setups for problems that use this remainder theorem. I have both of them in this video. All right, so the first one is more straightforward. We have a series here from 1 to infinity 1 over k squared. So this is a p-test or a p-series situation. So we know that this is convergent and the integral test applies. So we're going to approximate this using its fourth partial sum, and then find an upper bound for the possible error on that estimate. Okay, so first let's do the S4 part. So S4 is the sum from k equals 1 to 4 of this series. So it's the sum of the first 4 terms. So we have 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. Why don't I use a calculator to help me speed this up? This will be 1 plus a fourth plus a ninth plus 1/16. All right, and we get 1.42 and change. I'll just use 1.42 here. Oh wait, I can do this as a fraction. Hang on. So why don't we take this decimal and I'll do math fraction. I get 205 over 144. That's exact. So instead of rounding this number, why don't I do that? So this is 205 over 144. Okay, so this is my estimate for like if you actually added up these numbers forever and ever and ever, never ended, it would total roughly this number. Now, certainly because I'm missing the 5th and 6th and 7th, etc. terms, this is not exactly the full sum, but it's going to be our estimate. Right, so this is estimating the full sum of this. Okay, so that's the first half. Approximate this using S4, done. Okay, find an upper bound on the possible error. So now we're going to use the formula in the box here. So R sub 4 in this case will be less than or equal to the integral from 4 to infinity of the continuous function version of 1 over k squared, which in this case is 1 over x squared. And then just a reminder what R4 represents. This is the difference between the exact sum we're trying to estimate minus the estimate I made. So the smaller this upper bound is, the better, because that means this number is pretty close. Okay, so this is an improper integral. It's convergent, so I'm going to compute exactly what number it is. First, I need to put a limit up top, put b as the upper limit, limit b to infinity. I'll also write 1 over x squared as x to the -2 because I know I need to do an antiderivative. The reverse power rule on this will be 1 over -1, x to the -1. So I'm going to write that as -1 over x from 4 to b. Plug, subtract, and then I'll worry about the limit. Okay, so plug, subtraction between them. Now this part right here is my limit to compute. As b approaches infinity, this part goes to 0. So I have 0 minus -1/4. That comes out to +1/4 because of that double negative. So I'm saying, even though I only added up the first 4 terms of infinitely many, this is within 0.25 or 1/4 of the exact total infinite sum, which is pretty good considering how much work we put into it. Okay, let's look at the second problem type using this remainder theorem. So for the same infinite convergent series here, the question will change and say, okay, how high would the n have to be in this partial sum for this error to be less than 0.001? So I want Rn to be less than 0.001. Typically in these questions, they'll give you a very tiny decimal similar to this, and we just kind of work with it. Okay, so what we're going to do is say, well, I know that Rn is less than this formula, right? So I'm going to copy this over again. So I know Rn is less than or equal to n to infinity 1 over x squared dx. And I want that to be less than 0.001, right? So if I can choose an n that makes this less than that, then my Rn will be less than that as well. So I want to solve this for n, which seems like we shouldn't be able to do it because there's so much unknown, but this actually is completely possible. So what I want to do is compute this as far as I can with an n in it as the lower bound. And really, I can rip off a lot of the work I did up here, right? This 4 being a 4 didn't really do anything until right here. So I'm just going to kind of rip off what happened and say, okay, over here, it came out to the limit as b approaches infinity, -1 over b minus -1 over, and then instead of 4, it's just whatever n is. So I'm going to put an n there. I still want that to be less than 0.001. And again, still seems like we have too many letters, but this limit is 0, right? This limit we know is still 0 because b is approaching infinity, 1 over b will shrink. So whatever n is, this comes out to minus a negative, so it goes positive, 1 over n. And this is something that I can solve. It's a little bit awkward to do so, but that's okay. We can work with this. I'm going to multiply the n to the right-hand side and then divide the 0.001 over. So n has to be larger than 1 over 0.001. And I'll remind you, 0.001, this is the tens place, hundreds, and thousands. So this is 1 over 1,000. So this is actually 1,000. So my answer here is that as long as you take more than 1,000 terms of this series and add them together, you'll be at least this close to the exact correct